On this Tech Tuesday, we're going to be talking about electric aviation. Sometime later in 2023, perhaps the summer, perhaps the fall, the X-57, an electric aircraft in development at NASA, is set to take flight. NASA describes it as its first all-electric experiment aircraft, and it's going to look a little different than NASA has originally been advertising. Instead of 14 electric motors and propellers, the aircraft will have just 2. But those 2 motors are powered by more than 5,000 cylindrical battery cells in the aircraft's fuselage. If the plane does manage to take flight, it will do so in a form called Modification 2, which involves 1 electric motor and propeller on each wing, giving the aircraft the thrust it needs to take off. The team at NASA were hoping to use their later modifications to achieve the flight. They were forced to retrofit to Modification 2. Why? Well, because making a plane that flies safely on just electricity is hard.
Like, really hard.
And unfortunately, the program is only funded through 2023. Sean Clark, the principal investigator for the X-57 program, said this about the process. "We've been learning a lot over the years, and we thought we'd be learning through flight tests. Turns out we had a lot of lessons to learn during the design and integration and airworthiness qualification steps, so we ended up spending more time and resources on that, and that's been hugely valuable. But it means that we're not going to end up having resources for those Mod 4 or Mod 3 flights. The good thing is, it will still fly as an electric plane, but just in Mod 2 with 2 motors. One glitch the team have to tackle before the aircraft can safely take flight involves components that electricity from the batteries have to travel through before they reach the motors. The problem was with the transistor modules inside the inverters, which change electricity from DC to AC. Clark stated, "We were using these modules that are several transistors in a package. They were spec'd to be able to tolerate the types of environments we were expecting to put it in, but every time they would test them, they would fail. We would have transistors just blowing up in our environmental test chamber." A component failure, such as a piece of equipment blowing up, is obviously the type of issue that aircraft makers prefer to resolve on the ground, especially not in the air. In traditional aircraft, fossil fuels are burned to power the engines. This is obviously very flammable and explosive substance, but when controlled, it can produce successful results, like you see in every car and plane. Those working on electric aircraft powered by batteries need to ensure that the battery cells don't spark fires either. Last year in Kansas, for example, an FAA-sponsored test featured a pack of aviation batteries being dropped by 50 feet to ensure they could handle the impact. And they did. Beta Technologies partnered with Wichita State University to document the process, and as a big fan of watching stuff get dropped from a large distance, very solid work, 2 thumbs up. In the X-57, the batteries are a model known as 18650. The aircraft uses 16 modules comprising 320 batteries each for a total of 5,120 batteries. The key to success is making sure all these cells, modules, and batteries are packaged in the right way to avoid a fire, even if one of the batteries fails. In other words, failure is an option, but they definitely want to mitigate all of the damage that could happen, and they want to make sure that it doesn't start a blaze that would destroy everything.
Which would really just be like super heavy.
There's no industry standard on how they should be packaged, so it's not like you can just go with old reliable. But help came from above. Clark said they ended up redesigning the battery pack based on a lot of input from some of the design team that works on the space station at NASA. He noted that lithium batteries on the ISS, as well as in the EVA suits astronauts use and a device called the pistol grip tool, were relevant examples in the process. The key takeaways involved the spacing between the battery cells, as well as how to handle the heat if a cell did malfunction, like by experiencing a thermal runaway. Thermal runaway is a phenomenon that occurs when a battery is punctured and the heat and gases need to go somewhere. They do in fact run away. This can ignite all the gases and cause a major blaze that is very hard to put out. The team at the Johnson Space Center found it was beneficial to let the heat escape to the aluminum structure and disperse the heat to the other batteries in very small amounts. Sometime this year, the X-57 should fly for the first time, likely making multiple flights. This is a technology that is still in development, and it's not unrealistic to see this technology used commercially in the next 10 to 15 years. Personally, I'm very excited for this technology and what it has in store for the future of aviation. Thanks for joining us for Tech Tuesday. We'll see you next time.